The first thing I do also want to say is that this work is mostly work done by my student, Sebastian Dick, who is an excellent PhD student. And he's also a MOLSI software fellow and has been funding this. MOLSI has been funding his research for the last year and a half. So the work I'm going to be presenting as Kieran Burke introduced is really on the area of density functional development. And of course, I mean, one could, after seeing the work presented by Roberto Carr, one could ask, why do we actually need to put an effort on making density functionals more accurate if still the cost of calculating even doing DFT calculations, even at the sort of GGA level, generalized gradient approximation level, is still computationally expensive indeed, as Roberto Carr saw this. I think to remember that his deep potential method is several orders of magnitude faster than any DFT method. And we actually believe that there's still an important need to have methods that are in a way fully ab initio or from first principles, from which not only we obtain the total energy, but we can also obtain observables like the density and response functions that can easily help us make connections to experiments. Now, of course, many of the methods that we can compute, especially if we are actually looking at systems which have complexities, perhaps not that much at the correlated level, but more at the atomic structure level, meaning that we have very large systems, we have interfaces, we have large biomolecules, so on and so forth. Of course, we want to have accuracy in this sort of Jacob's ladder of going to the maximum accuracy in the density functional approximation. We want to go to this maximum accuracy provided by hybrid functionals and beyond. But of course, that's what we would like to do. What we always end up doing is staying in these ranges of approximation, because those allow us to compute systems of relatively large system sizes. And in particular, we are thinking on performing not only single point calculations, but we want to sample a complex potential energy surface. We have to do dynamics of systems of the order of hundreds or thousands of atoms for large time scales. And so this is how we actually started in this field. Actually, in my group, we've been doing a lot of work on liquid water interfaces, so on and so forth, and really working within DFT, but sort of at the edge of developing, trying to understand the physics of the systems, but also trying to understand what are the errors involved in our approximations. And so what I'm showing here, these are results from the group of Francesco Baisani, who works also at the interface, does ab initio calculations, but also development of force fields, on what you could call also machine learned approach, meaning like it's not neural network approaches, but certainly machine learned approaches, because what he's doing is fitting very complex potential energy surfaces to large amounts of data. And so what they did is developing a very, very highly accurate force field, which is MB-pole here shown, which was fitted to reproduce 2 and 3 body interactions at the correlated ab initio level. That means couple cluster, single, double, and triples. And they developed this field and this force field and compared this performance against all the family of density functionals, from the standard GGA ones to van der Waals functionals to hybrid functionals. So these families, these ones that you see in here, belong to the GGA family, some of them with van der Waals corrections. As soon as you see that this is the mean absolute error computed in a set of samples of liquid water, and is the mean absolute error as measured against quantum Monte Carlo calculations. And so what you're seeing here, all these four last methods in here are force fields, and the red is the most accurate result, which is MEPOL, the force field that they fitted, which really overperforms the any ab initio method, and is actually much less expensive, on order of magnitude less expensive than any ab initio method. So we actually were motivated by this. It's not like we wanted to move into the field of force field development, but we actually, what we thought is that all these exchange and correlation functionals that I'm listing in here were not developed to deal with a specific system. In reality, when we choose a specific exchange and correlation functional, we choose the one that works better for the system we want to treat. And so the question is, can we completely change this approach and say that, well, let's develop one which is as accurate as possible for the specific system that we want to treat, exactly in the same way as the force fields are developed. And so that's what we did. As Kieran introduced this morning, what we did is some sort of delta energy approach, meaning that what we're going to do is to start with a baseline exchange and correlation functional. The energy is a functional of the density. And so we can separate the contributions to the energy to all those which do not depend on the exchange and correlation energy, plus that which is provided by the initial exchange and correlation approximation, and plus a correction, which is what we aim to fit. And so we want to add a correction to reproduce a set of reference energies. And so I'm not gonna go into the details of this. This was itself it's also a machine learned functional from the point of view that we basically optimize an exchange and correlation enhancement factor to reproduce a very accurate data, in particular the data provided by MEPOL. And we did that by using the density as our representation, but not the density itself, but rather the momentum of the density, the Fermi wave vector, and the reduced density gradient, which has the natural variables in which these GGA functionals are represented. And so at the end, what we are doing is basically interpolating a set of reference exchange energies, which are nothing else but the projections of well-known densities onto a set of parameters, which are what we are going to optimize. And so by doing that within the functional form imposed by GGA functionals, we can basically end up with a numerical function for what is called the exchange enhancement factor, which is shown in here, which is is a term which depends both in the ratio between the reduced density gradient and the Fermi wave vector, and which determines all the final properties of our density functional. And by doing that, we saw that actually we were able to reproduce rather accurately the results obtained by MEPOL. Now, rather accurately, but still with limitations, because there is actually by imposing, by limiting ourselves to a functional form of this type, where we have an exchange enhancement factor, and we really don't allow us to look for all the possible degrees of freedom or combinations that the parameters that represent this energy can have. So that was our first attempt, or our first jump into the world of developing density functionals. And so we decided to go all the way through, say, okay, let's reduce all the, or free us of all those constraints imposed by standard forms, by moving into a machine learning approach. And so the question is the following. First of all, if we want to do it, we are still going to follow the same philosophy of developing a functional, which ideally we would like it to be universal, but we cannot make it universal because we don't have a universal data set. And so instead what we're going to do is develop a density functional optimized for a specific, very accurate reference data set. And of course, the main question we had is whether we can go all the way through to do it as general as possible and still achieve full self-consistent density functionals. What I showed before is fully self-consistent because I'm forcing myself to remain within a very well-defined functional form. So we started, and instead of going all the way, the question is what are the features or the representation parameters that I need to include in this density functional, which of course we know that it depends on the density. And so the question is how do we take this density and make it a set of features to learn with our machine learning. So we call this informed machine learning for maximal extrapolation. And in a way, we, rather than entering all the raw data in an unbiased way and what it means raw data, in reality the raw data will be just the external potential, which is nothing else but the atomic positions and in the atomic species. So rather than giving this as the input for my potential to learn, what we are going to do is to pre-process this data and to select the most relevant data out of this raw one, meaning that what we are going to do is use DFT as a preprocessor to generate a density, which of course still, first of all, is not the exact density, but it already contained a lot of information that we can now make our neural network engine learn. And so the other thing, of course, we want to train on a small, and we need it to be a small set of data. Small from the point of view that still we need to have highly accurate data. That means that we still need to do very expensive high level ab initio calculations and not on small systems. So in principle, we want to have highly accurate data on the molecules or solids that we are studying. And hence it should be as small as possible, but it should generalize to unseen data. And what was even more important is that in the moment you move out from a representation or a standard representation of your density functional with a specific functional form, and now the density is your variable. The question is how can you do it so as you make it arbitrary? It can be valid for any system size. So I don't want to learn a single molecule, and then if I have a solid of that molecule, I don't want to have to increase the size of my neural network. So it should be generalized for any system size. So this is the sort of the change of paradigm. In the previous method that I presented, PPS, so what we had a density which was always represented on a fixed grid of Fermi momentum and reduced density gradient. And that grid, so if this is the density of a given molecule, but if I have n molecules and I now represent this density in this space, Kf and Kg, you won't see a change. It's basically well limited and constrained. So it's completely independent by the system size. Now, how can we do this in a machine learning approach? So we change the paradigm, that's the first thing. So we are going to learn from the density, but we're going to learn atom by atom. To do that, we'll need to choose the right network and architecture, and of course, we'll need to choose the best set of atomic descriptors. And these descriptors need to of course, satisfy all the necessary symmetries, which are permutational symmetry of exchange of atoms of the same species, and then of course rotational and reflection symmetry. So the first part, the permutational symmetry, was sort of straightforward to impose because this is a problem that had already been thought in the field of force field development. So this is we chose an Wheeler-Parginello type of network architecture, where we basically, what we are going to calculate is, given a given density, what is the correction of the energy that we need to add to get the total energy of the system equal to the total energy as computed with highly accurate method. So what we are going to do is we start with a set of atoms or species, And each species is going to have its own artificial neural network, and which is going to produce a local energy. And what we are optimizing is not these individual local energies, but the sum of the total, the sum of all these local energies. This is exactly the same of what's done in the area of atomistic force field development. So we have solved the problem with taking this approach. We basically already solved one of the problems, which is the extrapolation to large system sizes, because now each neural network, which is specific for one species, is repeated and replicated for as many atoms of that species that we have. And so system size scales perfectly. Now the question is, of course, still the density needs to be represented. And so we can either choose do some sort of width-based or a basis set expansion. And what, as I'll talk, so this is basically what we are going to talk about, and that's going to take care also of satisfying the remaining symmetries for the problem. So this is part one. And this, of course, part two is that still we are solving a problem-specific solution, meaning that what we are going to do is optimizing a functional for specific data set. So it's not a universal functional, but we'll see how can we basically move in this path from a data set specific to sort of universality. And we'll see how indeed the method itself offers and naturally presents transitions towards a more transferability, a universal behavior. I do want to say before I start that, of course, this is not the only approach. I've chosen here, I think, are the three most representative approaches that are similar to what we do. So Kierenberg presented the method that they worked on, where they map the potential directly, from the potential they obtain the density. A problem of the method, as he presented, of course, is that the size extensivity is not straightforward to achieve. And then these two other methods by the Japanese group, this paper was actually recently published. I put on the archive reference, and the group of MERT4. They have two approaches also. This one is grid-based. This is basis set-based. This grid-based is more on the line of what I started presenting at the beginning, the PPH, but going beyond on local moments of the density distribution. What none of these methods have, except for this one here, is the fact that they can be done self-consistent. So these features, so we have the density, and we want to get the input features for our neural network. We want them to be satisfy rotational and reflection symmetry, and they have to be representative of the density. So what we are doing, and we started working with the code siesta, although now the method that we have is rather general. It works with siesta, it works with PySCF, and the way we are moving forward is to have it to be a set, a library similar to libxc, but going neural XC. Well, it will work independently of what is the basis set that the underlying DFT code uses to compute the underlying exchange and correlation potential. So we are going to use atomic orbitals as the representation for our density, basically. We started at the very beginning, we indeed started in the representation space of the density matrix. So basically, this is the density matrix in the representation space, where these in here are the numerical atomic orbitals, which serve as the basis to solve the consum problem. Now, if we take the diagonal sum of this density matrix times the overlap, what you obtain is that's what is called the Mulliken charges. And so one can look at local atomic charges, or these Mulliken charges, which, as I say, is basically the trace of the density, the local density matrix times the overlap as the representations. Now, the problem that these representations have, as we're saying here, is that they do not transform as tensor. And so it's relatively complicated if we want to impose rotational symmetry, because we have to apply it to the full overlap and density matrix first. And that was the first and the most important drawback. And also there is not easy or straightforward, if you want, path to symmetry. Now this we'll see in, I think it's in a couple of talks by Lin Feng Tang, they have actually done a similar approach where they've been able to go through this problem, not in the way that we do, but really by using so achieving this symmetry using the eigenvalues of this local density matrix. Instead, so what we went back is basically expand the electron density around each atom in a set of basis functions. So this is our expansion. It's a linear combination of real spherical harmonics time orthogonalized radial functions. So these are our electronic descriptors. Basically, we project our density into these density basis sets. And now we can symmetrize, so the step of going from here to here allows us to achieve rotational invariant by summing the quantum numbers. So now is here where we get the symmetrization of our descriptors. And then the targets that we are optimizing to is the difference between the reference energy, which at this point, I have to say, this first part of the talk that I'm presenting, we were still thinking very, very narrowly on, we want to obtain a density functional that works for water. We were not thinking of self-consistency. We, in a way, were thinking like, how can we do some delta DFT approach and correct our density functional still without having to give up all the underlying DFT calculations. So our goal is not having a more efficient calculation, but having a more accurate calculation. So these are the results. Now this is, as I said, this functional is not self-consistent, meaning that we do a DFT calculation, and over the final DFT functional, we basically, in the final density, we obtain, we apply our trained machine neural network or species-specific neural network, and we add a total energy or a correction to the total energy. And so what you're seeing here are results for liquid water. These are in blue is the baseline functional, and in yellow is our results, the baseline functional plus our, what we call at that point, machine learning correcting functional, which corrects very nicely the two-body errors and then also the three-body errors. These are the energies of clusters, hexagonal clusters of water molecules containing 6 water molecules, which are well known to be very difficult to, the total energies of these different configurations are well known to no density functional be able to represent them or order them correctly. And what you're seeing here, so again, this is our baseline functional, and this is the reference, and the reference is as accurate as the coupled cluster calculations, because it's being fully fitted to reproduce those results. So we reproduce the right order, and even more, even though we are training only on single monomers, dimers, and trimers, we are able to reproduce energies with a really small error. So what you see in parentheses is the underlying error of the baseline functional, and here is the error of our functional plus correction. Now, of course, the limitation of what I just presented in here is that we really don't only have a method to obtain a correction to the functional, but we do not have, if we want to correct the forces, we cannot get the gradient. So indeed what we did in our first work is to have a second model for the forces very similar to what is done in force field developments. So that was the first work, but then we realized that indeed we were very close to go all the way to have a full self-consistent density functional from which we actually can calculate naturally. Once you have your full self-consistent density functional, you can obtain the functional derivatives, obtain the potential, and once you have the potential, obtaining the forces, stresses, so on and so forth, is in a way almost straightforward. And so let me go step by step from what we're doing. So you start with a baseline functional. You do a DFT calculation, so now you're going to project onto, you said that the basic function is exactly the same, this instead of orthogonal atom-based functions, which is species dependent. you symmetrize these descriptors, and you obtain a machine learned energy, which is made up, of course, of the sum of atomic contributions. Now, once you are in here, that's where we were before, but it's actually natural to go all the way in this direction and obtain the potential as the functional derivative of this machine learned energy, which is nothing else but the derivative of this energy with respect to the symmetrized, and then we unsymmetrize this derivative. And so once you have this potential, which is expressed as a linear combination, as you see here, is nothing else a linear combination of a set of coefficients, which are the derivatives of this energy with respect to your underlying machine learned coefficients, times the basis set functions that we use to represent the density. And so the total final machine learned potential is added back to the baseline, in this case is PV, and you have what we call an NXC potential that you can treat exactly in the same way, or you can use in the same way that you use for any DFT calculation. And so that means that now we are starting from a baseline potential to which self-consistently we are adding the correction, and of course we end up in a local, in a minimum or an absolute minimum with a potential which produces also a change density. So the density that optimizes this potential is different than the density that optimizes the baseline potential. And what we did after this, of course, we still optimize it for a set of databases for a specific system. So we want to check the transferability. So in this case, what you're seeing here, we train in a database with a set of ethane and propane molecules. So ethane and propane here, 2 carbons, 2 fully saturated and 3 fully saturated carbon. And then check how is the performance. Of course, here are the errors. How do they perform in the case of propane and butane, butane and isobutane, which were not included in the training. And the errors are really small because the chemistry environment is similar. They're all single bond descriptors. If you now look at actually how does it perform in molecules like ethylene, propene or acetylene, which now they have double and triple bonds, you see there is an underlying systematic error, which comes from the fact that actually we didn't train on chemistries that these molecules have. However, it is easy to show that you increase just your data set by training data set with just a small number of structures. You can see that the R-square coefficient, which is provided in here, it can be largely reduced. So this transferability, I'm showing exactly the same in here. So those numbers are training these are propane and ethane molecules, so 50 propane and 20 ethane, and then 10 propane, 5 ethanes. And these are the errors that this neural XC functional performs against the accurate data as compared to functionals, general functionals, PV, scan, this is a hybrid functional. All of them have errors in systems that they were not trained against, which are smaller already than general functionals that are universal in a way. And the same I'm showing here, this in case we have a functional which was fully developed for water, and it has also a large amount of transferability, as we will see. First, it was trained only on a set of monomers, dimers, and trimers, but we evaluated it in condensed phase. And so in terms of the liquid, is the one, so our functional is in green. Sorry, it's in black, in dash blank. In green is what is MBPOL, and experimental data is in here. So we obtained the same results or very close to MBPOL, but even more, what you can see is that we didn't train at all for breaking bonds. What you're seeing here is the proton transfer and energy barrier for concerted proton transfer around an hexamer ring. As Kieron Burke introduced this morning, these actually in general density functionals really perform very badly. So this is the barrier that reproduced by PV, scan, and a hybrid functional. And we are basically at a couple cluster accuracy. These are hydrogen bonds for systems that, so this again, this was a function that was only fitted for water, but then you look at how it performs for this is for the S66 data set. And so these are the errors for our functional versus PV. And these are molecules that have never been trained in the functional, and the functional itself works extremely well. So I'm about to finish. Yeah. I just have a couple more slides. All I want to say, and I didn't have that much time to this, is that of course it works extremely well on obtaining total energies. The question is, how does it do for densities? Does it improve on charge densities? And what we've seen is that it does improve, but the improvement is really small. I mean, you can see it in here. These are for water molecule. These are the difference in charge density between coupled cluster and PV, and between normal method and PV. There are improvements in the right direction, but definitely is not there yet. And so what we proposed in our paper, and is the direction what we are exploring now, is that indeed there's no reason why the densities will be well reproduced, because we didn't impose that. But we can actually do that by fitting to the exact potential. And so if we have the exact potential, we can include it in our loss function. And then with that, if the imposing that the exact potential is satisfied also, then the density in principle should also be reproduced. And that's what we saw in here. So this is the hydrogen molecule density with PV, and this is the hydrogen molecule density with our neural XC, imposing that the loss function also minimizes the error with respect to the exact potential. So, okay, these are my conclusions. So this is, in a way, is a pathway to work towards universal exchange and correlational functional development. There's still a lot to do. I think this direction is very promising, especially if we can include the reference potential in the training procedure. Then we'll be able to achieve both energy and density, and probably going towards a more universal representation. So thank you everyone for listening.